You see it all the time, right? These headlines about groundbreaking new theories, wild scientific claims. But how do you know what's real? How do we actually separate a true scientific breakthrough from what's, well, just a good story? Today, we're going to break down a framework for doing exactly that.
So, let's start with a pretty provocative question. Is modern physics broken? I know, it sounds super dramatic, but it's a question that a lot of people inside the field are actually asking. There's this growing feeling that maybe, just maybe, the discipline has lost its way a little, creating a space where some questionable ideas can get a foothold.
And this quote right here, it just nails the core of the problem. Physics today often swings for the fences. It tackles these huge, almost philosophical questions. Now, the issue with that is, when your theories are about things you can't possibly test, you're left with these really compelling stories that might not actually be science.
So, where does that leave us? Well, it puts the field at this really strange crossroads. On one hand, you've got these incredibly successful models that describe our universe with just stunning accuracy. But on the other hand, you have this kind of dubious state of affairs where new ideas are popping up all over the place, and they really struggle for legitimacy.
And here's the paradox of that success. Our best theories, I'm talking the Standard Model, general relativity, they are phenomenal, but they're also incomplete. They have known limits, unresolved problems, right? And that incompleteness, it creates this opening for new theories to come in. But it also means a lot of these new ideas are frankly built on some pretty shaky ground. So, before we can even begin to test a new idea, there has to be this really crucial shift in mindset, a move away from making these grand, sweeping claims and towards something a lot more grounded. You could call it a call for humility.
This comparison, man, it just gets right to the heart of it. The old way, this sort of arrogance, was all about claiming perfect exactness and going after those huge, untestable questions. But the new humility, the path forward, is about accepting that science is always approximate. It's about digging into the small places where our current theories don't quite line up and rigorously, painfully, forcing your numbers in your mouth to match the real, messy world.
You see, it's a complete philosophical reset. Real progress isn't about finding that one final theory of everything. No, it's about the patient, humble work of just getting a little bit closer to reality, one approximation at a time.
Okay, so with that new, humble mindset in place, how do we actually do the work? Well, the source material for this explainer lays out a super clear, really tough, and totally non-negotiable framework. Think of it as a 6-step gauntlet that any new idea has to survive to earn its legitimacy.
And this is the roadmap. First, you need a crystal clear conceptual description. What is the core idea in plain language? Then you translate that into the unambiguous language of math. Now, crucially, you have to define what proof even means compared to our current best theories. After that, you design a test, you build the experiment, which often means writing software these days, and then finally, you execute it and you face the data. For someone with a radical new idea, this is a long, lonely, and really tough road, but it's what makes the science sound.
And here's the thing, and this is maybe the most important part. You cannot skip steps. This is a hierarchy. It has to go in order. You absolutely must have the conceptual grounding before you start building the complex math. Rushing ahead, especially jumping to the engineering or the experiment without a solid foundation, well, that is exactly how we end up with all those dubious claims we talked about at the beginning.
Okay, so let's talk about that fifth step, experimental engineering, because in the 21st century, that looks, well, a lot different than it used to. The laboratory for many of these new ideas isn't a particle accelerator anymore. It's a computer.
I mean, this is a huge fundamental shift. Today, physics engineering is deeply, deeply intertwined with software engineering. Before you can even think about building some kind of physical machine to test your idea, you first have to build a virtual one, a software model that can simulate your idea and see if it even holds up.
And the logic here is just so powerful. First, you build that numerical model. Then you use that model to create a kind of virtual reality, a little digital universe that runs on the rules of your new theory. And then, finally, comes the moment of truth. You compare the results from your virtual world with data from real-world experiments. Does your simulation actually behave like our reality? You have to understand, in many cases, this simulation isn't just a helpful tool. It is the only way to know if an idea has any merit at all. It's the ultimate proving ground where theories either start to gain legitimacy or they fail.
All right, so let's pull all of this together. What does this all mean in practice? We've talked about the problem, the right mindset, and the process. It all comes together in this really practical toolkit you can use for evaluating any new scientific idea you come across.
Think of this as your legitimacy checklist. The next time you see some big headline about a radical new theory, just run it through these questions. Is the core idea actually clear? Is the math solid, or is it built on shaky assumptions? Have they actually built and tested a numerical model? Does that model match reality? And hey, can it still explain the stuff we already know works? And finally, does the work speak for itself? And that last point, that might be the most important one of all. In the end, it really doesn't matter who proposes an idea. They could be a celebrated genius or a total outsider. What matters is the rigor of the process. The work has to stand or fall on its own merits, validated by this transparent, repeatable, and honest method. So I'm going to leave you with this question to chew on. Armed with this 6-step framework, take a look at the landscape of modern science. From string theory to alternative models of gravity, which ideas out there are just telling a really good story, and which ones are truly putting in the hard, humble work of earning their legitimacy?